Hello, can you help me? So this is the quick revision and also math tutorial, and also we're trying to narrow down what we can just make your life a bit easier. Okay, so let me change the color here. Okay, so we are actually dealing with this quiz 2. Okay, so it's all coming from until what we have taught today until the tutorial 2. Okay, and so you can see these are the general requirements. I have the general knowledge of the ceramic materials. So the process, so we learn process, we learn a structure, right? So property, we're going to learn next week. Okay, and specific knowledge on processing. So we spend a lot of time explaining about the processing, and also the how can we enhance the properties by using different process, and also by enhancing its microstructures. Okay, and this is a first week. So this one is not required. So the characteristic of ceramics and applications is not required. Okay, so can you cross out? Can you cross out? Okay. So let's just move on. So we set objective, so chemical bond, the concept of crystal structures, and also the minimal RA, and what is the crystal structures of some typical ceramics. Okay, so there's a 3, right? We mentioned actually 4 of them, and also understand the chemical characteristic. So this one is not required. And okay, so for the definitions, all these are simple and straightforward. Okay, so like this one is not required. Okay, but anyway, this is just some common sense, and this one also very common sense, but there's no need lah. Okay, and these are the forms. You need to know all these are different forms of ceramics, and this is needed. So what are the subatomic, what are the atomic level? So and nano level and micro level. Okay, so these are the big pictures. So when we talk about ionic bonding, so we are talking about this the difference between the electrical activity. So know this concept. Okay, and then okay, so ionic, I think you know everything, right? You learn in your high school. So the covalent, and these are the ionic. So these are the covalent. Okay. So I think all this you learned before, so it's just a very simple thing here. But of course, it's not focus of this course, right? The focus of this course is ceramic, is partially ionic and partially covalent. Okay, so these are the essence. Okay, why it is important? Because later when we determine RC over A, right? So you realize RC over A only applies to very ionic case. Okay, if you have a little bit more covalent bond, so that RC over RA table cannot be used anymore. Okay, so these are the essence of this course. Okay, and what is crystalline? What is amorphous? And there's 7 unknown. I think you learned it a long time ago already. So these are a different atomic level, but you should know, right? So when we talk about atomic, which means you determine crystal structures. So crystal structures have 7 different types, but the exact things like simple, all these things, because it's not needed in this course. Okay, this one needed. Okay, structure. Also, this one needed. So what are the microstructures? Okay, so like a shape and size of the grains and the pores and any second phase and all other distributions. So these are needed. Okay, and what are the traditional advanced ceramics? So this one we need. Okay, move on. Okay, so summaries are always the important thing here. So we're busy. Okay, but anytime all these are just summaries. So which are the important things? But if you really look for the correct answer, please go back to the test. Okay, so this is just like outline thing for you to remember. Okay, like key points. Okay, so what are subatomic, atomic, and nano, micro? Okay, so these are important things because almost all these summaries are the important concept of this course. Okay. And also the factors affecting the crystal structures. So we said these 3 things are the important 3 things. Okay, so we said this stoichiometry, which actually equals to this charge balance. You have to have the charge balance. Okay, so then we have another concept which we call coordination number. So this coordination number is related with these stoichiometries, and also this RC over RA. Okay, so RC over RA, so normally ions are bigger and close packed, then followed by the chi ions, which are normally in the middle as an intercept. Okay, and this is also important. Okay, important thing to understand. You have to have in contact, and also this is the minimum case. Okay. Okay, and this one, okay, is actually we spent a lot of time to derive this case, right? This one we have derived, and also this one we have derived. Okay, so then should be okay. So all the rest, only the one required in the class and tutorial is so how to derive is not required. Okay, how to derive all these numbers is not required. Okay. It is not required, okay? So although we have explained some of them in the class and in tutorial, but how to derive them is not required, okay? Not required, okay? And also this one is 6 case coordination number. So as I said, so we have derived this one in class and derived this one in tutorials, okay? But it's not required, okay? It's because it's just simple geometries you have learned in your high school, okay? And also, this one is important. Some student feedback looks very dodgy, right? But actually, if you read, in many compound, tetrahedral coordination is observed. Tetrahedral coordination is something like this, which means your coordination number is equals to 4. Okay, so if you rephrase with your own words, it's something like this. So in many compounds, actually, the coordination number is 4, despite the fact the reduced ratio would predict otherwise, which means what? From this RA over RC table, so maybe the coordination number is supposed to be 6, okay? But it's not 6 anymore, so it is 4. Okay, so this is more like a plain word, okay? So what I get from is from the textbook. Okay, so textbook always write something like this, okay? So why this will happen is because when you have more covalent bond, so you are going to have, you will observe this one. Okay, so for example, if you have the ion polymerizing power, so more or less like if you have more covalent bond, so this is going to happen. So SP3 is not covered in this course, okay? Then continue, so rock salt. What is the rock salt structures? So please remember, because it's very often used, so often used, okay? And also what are the cesium chloride structures, okay? So it's also very often. And also zinc blend, also need, okay? And okay, so let's continue. Okay, so we give you this example, which is zinc blend structures, so which fulfill this case, which is this tetrahedral coordination, which is coordination number is equals to 4, okay? So, and also perovskite, AbO3. So how this AbO3 looks like, because it's so often used in material science. Okay, so please know it, okay? And also this is chemical bond AbO3, okay? Like all these details, of course, no need, right? But the structure, please remember, okay? So perovskite, yeah. So where are they? So you need to remember, okay? And also this one is important. So if the atoms they stand in the corner, edge and face, so it's supposed to share with neighbors. So how many neighbors are there? So you have divided, okay? For example, 8 people share with 1 atom, so you have divided by 8. So if share by 4, you have divided 4, 2, you have to divide it by 2, okay? So this is again very common knowledge for material scientists, okay? And this one is okay, so we have already explained, right? Okay. Another summaries. So charge balance, big 3 things, IC over RA, and also this ionic bond, this one bond. Okay, so these are the simple version. Okay, so just keywords. Please use the correct version in the main text. Okay, and also the rock salt is something like this, cesium chloride something like this, zinc blend something like this. Okay, and also what is perovskite? So it's something like this. Okay, so all this you need to remember. So this one is not required. Okay. So this is chapter 1. Okay, so let me trying to find the chapter 2. Part 2. Let me see. Part 2. Okay, so which is this one? Okay. Okay, so I share. Hey, did I record? Oh no, did I record? Let me check whether I record or not.
Record.
I have recorded. Okay,
Yes.
can. Thank you. Because I forgot once. Once you forgot, once you will never forget. Okay, let me check. Okay, I recorded. Okay, thank you. So can you see this slide? The new slide? The part 2? Okay, thank you. Part 2, so process of ceramics. Okay, so now we move to the part 2. Okay. So for this one, so we start with introduction, the powder synthesis, and also the sintering. This is always the VIP. The sinterings are always VIP. Okay, so what you need to learn is the basic rule of processing ceramics. Okay, this is of course right. You always remember as a bigger cake, and what happened in the solid state. So actually, these two are very similar. Is because the solid state reaction is always start with ball milling, then sintering, right? So it's the same thing. So understand what's liquid and solid. Okay, and also this is important. Understand what is occurring during sintering. So what is magnesium pass or particle frequencies? So now if you read back, I think you know everything already, right? What are 5 atomic mechanism? So what are the factors determining the sintering products? So what are the various mechanisms in liquid? So you have different steps, okay, like all these things, relationship, okay? So once you read through, then you know what we have already learned. Okay, so this one needed, okay, okay, and then this one needed, okay, and this no need. I don't really require you to remember all these things, okay. And since in this solid state, we only talk about ball milling, so this is just ball milling for the powders, okay, so no need. For the rest, I mean, there's so many ways to make particles, so there's no need. Okay, so these are the what is ball milling. Okay, so what are function of ball milling? Okay, and also so the ball milling, what are the possible problems such as elastic plastic deformation, welding, and you may have the particle fracture and fragmentation, but you may also have the elastic and also the welding. And also you will know that when the particle become too small, so the stress will be too high. Okay, so which means when the particle becomes smaller and smaller and smaller, actually the stress you need to break down it will be even more difficult. Okay, so this one just share with you the stress will become very, very large if the particle size become too small. Okay, so which means if you really want a mill to very, very ball milling to very small size, it will be actually very difficult. Okay, and also this example, one example is good one for you to understand the whole process of any like a process of the processing. Okay. Okay, process structure and properties. Okay, and this is a good example. YbCO. So this is a Nobel Prize winning materials. So we told you. So it's but you just the process is pretty simple. Okay, so please know it. So there's no need. Okay, good enough. So actually this one, right? So the tutorial question. So we said that there's 6 steps. So it's not required in the final. In the CA. Okay, I'm not requiring you to know all this because I just want to explain it because I realize students still make mistakes when go to the lab. So this course is also partly served for the purpose of FYP. Okay. And all these are the take-home points, right? What is the basic root? What are the ball milling function? What is the function of the ball milling? So what is the classical solid state reactions? A plus B equals to AB. So you need a bit post-treatment to tune the stoichiometries, okay? And then we move to important one, sintering. So what are the sintering? So sintering is this, and this, okay? But compared with metal and polymer, so it's very different because the temperature is very high, super high temperatures, okay? So what are the goal, okay? And so these are needed. So what are the 2 different type, liquid and solid, okay? And also this is the conditions for densification to occur, right? This is pretty straightforward, okay, because from this equation, you can get this condition very easily, okay? And no need. Can you cross up? No need. Okay. So which means also the tutorial question is also not needed. Okay. No need. So what is the driving force? You need no, right? Because it's just also no need. Okay, so this is the two routes. So the route 1 is for densification, route 2 is for coarsening. Okay, so this is the essence of this course, right? So the thing is, if you need a serratic one, please try to suppress this coarsening. Okay, and so all this like a real thing, no need. Okay. And so this one is also one of the examples. So you show you what is this one so densified, this one so porous, right? So just let you know. So this is a real picture you will see in your FYP or whatever. Okay. And also keywords, I'm gonna go to centering, driving force, and two roots. Okay. And the derivation, no need, remember. So remember these equations. But anyway, if I'm testing you the equations, I will give you. Okay. So what? Since you were able to understand, Yongjing asked to clarify for YBCO, the example, I think you will be answered. What do you mean? So for that one, actually, it's just share with you. So you need to do the post-treatment to make sure this oxygen a little bit more. Okay. So this one is, of course, the details, for example, so how many yttrium, how many copper, this one is not it. Okay, but that one is a good example to share with you that how can we tune the oxygen. Okay, so continue. Okay, thank you. Okay, so all derivation is not required, okay. I mean the derivation itself is not required, okay. I'm not saying this equation is not going to require. This equation is so important, right? Because this is the essence of the whole course. Okay, so, and again, this are not needed. Yeah, no need. Okay, no need also. Actually, there's no point in know all these details, right? Because all these conversions you can get easily from the website. Okay, but it's really you do it by yourself in the exam is quite weird. Okay, and take-home point always very important. All the take-home point are the most important thing. Okay, I think you have all of them, right? You should have already seen the videos of all the. I have uploaded all the video. If you haven't seen it, let me know. Okay, all the video, all the answer I've already uploaded, and later I'm also going to send you this link. Okay, so then everything should be ready, should be there already for good enough for you to review. Okay, and no need. This one no need. Okay, no need, no need. All the derivation is not required. Okay. As I said, you know, the derivation, so I explained very clearly in the tutorial and also class. So I do hope you to know it because this is quite a basic thing for material scientists. Okay, if you need to do any calculation later stage. Okay, so and also this one only. Okay, so this is important. It's no need. And also this viscous one is also not needed. Okay, it's just an example to share with you. How can we do the calculations? Okay, how can we understand what is solidification? Okay. So need. For this one, although the equation is not required, but this is very important. This is very important. Okay. And also this is a concept, what is densification, right? So I think I already stressed twice already in both class and tutorials. So I do assume all of you understand already, okay? And also compared with faster diffusion. So basically, so this one is saying if you have too much surface diffusion, which is P2, so then you will definitely have the coarsening. Okay, so if you want P4 and 5, so then you will have densification. Okay, so this is only coming from here. So which means normally your grain boundary diffusion is higher than the surface diffusion. So if you want densification, so you need bit higher temperatures. Okay, so this is examples to share with you how temperature is going to influence the densifications. Okay, so let's continue. And this stage, since I did not explain, right? I did not explain, right? Am I correct? So initial stage, intermediate stage, final stage. Okay, it's just how the start. Okay, so these are the real thing. No need. Okay. All this. So that's why we need all these equations, because all these equations is going to tell you what is the rate. Because as I said before, P1 to P5 is going to happen all the time. Okay, so we have 3 stages, right? So which means in one stage, you are going to have 5 mechanisms running at the same time. But in the end, which one is going to win? So you have to calculate. You have to calculate its rate. So this is a rate. Okay, so whichever faster is going to win. Okay, so that is the whole essence. But we did not include all this. So all this only required for PG class, because I'm also teach the postgraduate course. And this is required for the PG, but not for the undergraduate. Okay, so then no need. So no need. Okay, because all these are too details, too much details there. Okay, so general remarks, please remember. These are something like after all these calculations, there's some general remarks. Okay, so this helps you to make decisions. When you do any centerings. Okay. And no need all this. Okay, also no need. Summaries. Okay, summaries. Driving force, which stays, 2 roots, cosine densification. Gas of excretion tells you this. Okay, 5 atomic. Okay, so all these are P4 and P1 to P3. And so this is P4 and P5, give you densifications. Okay, so then we also, these are the sum of the factors like temperature. So again, this is coming from all the calculations used as a guideline. Okay, so activation for bulk is largest, surface is grain boundary followed by grain boundary followed by the surface. Okay, so in order to have higher densifications, make sure you have a bit higher temperature. So grain density need to be higher. Okay, uniformity of grain structures also need to be higher in order to have higher densifications. Okay, atmosphere is not needed, because I don't think it's a case-by-case studies. So that's why we did not really talk about it. It's not like you add certain atmosphere going to give you exact end results, but it's case-by-case. Okay, you can read through. So if you're really doing the centering for your FYP, so you can always refer back to these notes. Okay, and size distribution also easy to understand, right? So if you want uniform, you start with uniform. If you start with abnormal, you end up with abnormal. Okay, and for this impurity, we only explain one, so which is suppressed green growth. So which is this one, okay? So which means once we add a bit impurities, so these impurities will stay in the grain boundaries to suppress green growth. So make sure the green growth happen later stage. Okay, so this is because this is a very good example to share with you, to have you to let you have these feelings of what is really going on in the century and how these impurities helps to suppress the green growth, making more densified. Okay, so this is a very solid example to let you to know what's going on in the centuries. Okay, and also the particle size in principle, if you're smaller, will be better, right? Because you start with larger surface area, but in practical, because it's going to agglomerate. Agglomeration is always not wanted because agglomeration is very difficult to control. Okay, so and also become very ununiform. Particle size will be very ununiform at the very beginning, so you will have a lot of issue later. Okay, so normally we always need to reduce the agglomerations. Okay, so summaries. So we just explained this one, and also then this general points like this one explained. This gas, no need, and all the rest. So you can just use it. Okay, so except the gas we did not explain. So then the liquid, so we actually have tutorial already. So what is liquid are important. So why liquid is good? Because they have this extra, this gamma LV capillary force. This capillary force, you change. So we said this is a very non-wetting case. You can see a bubble, just all this become a bubble. Okay. So then this one help you to understand what is this theta larger than 90 degree and less than 90 degree. Okay, so all this calculation is not required, but the graph is very good for you to understand what is this large attractive force when you have a liquid phase. Okay, so this is a very good example to share with you. Okay, and also these are the 3 stages of this liquid phase sinterings. Yeah, so just remember it. Okay, I think only this one is a bit tricky, right? But I explained already, right? So basically, you can see I read is a bit difficult. Dissolution atom at the contact point. So contact point means green boundary. Okay, so the green boundary, the atom at the green boundary will actually move to the contact area. Okay, okay, move away from the contact area means move away from the green boundary to where? To where? To always to the neck. It's always going to. Okay, so sometimes the book, these are all from the textbook, so you might need to find a big way to understand it by yourself. Okay, and also we also mentioned diffusivity in liquid. The atoms, the diffusivity of atoms in liquid is orders of higher than those in solid, right? So we said in solid phase, actually it is because you have to move through the vapor. So as we explained in the tutorial, you use milk powder for you to understand this. So milk powder will be much easier to move through the water, right, compared with the vapor. Okay, so that's what we are trying to say. And step 3 is just solid state takeover. Okay, and desification. So these are the 4 conditions. So it is also very important. Okay, so in order for desification to occur in the liquid phase sinterings. Okay, but we said so the bad thing is here also important. Okay. And these are the property and microstructure relationship. So as I said, this one is not required at this moment. So all the rest, please remember. Okay. Maybe not this one, no dielectric, no need. So all the rest, please remember. Okay. These 2 are not needed. All the rest, please remember. Okay, so then yeah, this is a good example to share with you how a nominal, if you have different structures, will give you different properties. So you can see, okay, it's very good examples. So then this sintering, which are all these are takeoff point. Okay, so large capillary force. Okay, the function of large capillary force is this, and these are the 3 stages, and also 4 conditions need to be met, and also in many applications could be very harmful. Okay, and property is very much microstructure dependent. Okay, so that is all. That is all for the CA2. So remember CA3. So all these things won't be tested again. Okay, so please try to clear everything by this Friday. So then you can move on and leave this behind. Is it clear? So don't just like skip the CAs. This will only add up your burden later. Because I understand in week 13, you have so many CAs. So please clear this part and move on and clear it. Thank you. This is super important. Okay.